Hey everyone, I'm going to go through the 6 problems on your exam number 3. I've already graded it and I've posted the answer key as well as emailed you a copy of your graded exam, but I wanted to go through the problems so that you would have a video you could look at to see how each problem is done. So we're going to start with problem 1. This problem asked you, given the function f of x was 81 minus x squared, use the midpoint Riemann sums on the interval from 2 to 8. With 3 subintervals, so n is equal to 3, and we were looking to approximate the area under the curve for my f of x function, 81 minus x squared. Okay, if I'm making 3 subintervals from 2 to 8, this interval has a length of 6, so if I divide it into 3 subintervals, I'm looking at a width of 2 for each subinterval, from 2 to 4, 4 to 6, and 6 to 8. So if I'm going to sketch in those rectangles, okay, I'm going to be drawing, and I'm using the midpoint, which means that I'm looking at the middle. So I'm looking at 3, at 5, and at 7 to get the height of my rectangles. Okay, so I was expecting in your drawing that you would draw in a rectangle with a height at the function value of 3, with a height at 5, and with a height at 7. Okay, so your picture on the right for full credit should have looked something like that. Some of you did a left-hand sum or right-hand sum picture. I was looking for the midpoint picture because I asked you to find the midpoint here. To approximate the midpoint sum, okay, I need to do the width, that's 2, times the area evaluated at 3, plus 2, that's the width, times the area evaluated at 5, plus 2 times, that's the width, times the height, which is the area evaluated at 7. And so if I plug 3 in here, I get 81 minus 9. That was a height of 72. If I plug in 5, I get 81 minus 25. That was a height of 56. And if I plug in 7, I get 81 minus 49. That was a height of 32. So I multiply and add these up, and my approximation for the area under the curve was 320. That's problem 1. Okay guys, so this is problem 2. 2a said the limit as x approaches 0 of e to the 3x minus 1 over 5x squared. If I plug in x directly, the limit as x approaches 0, I get e to the 0 power, that's 1, minus 3 times 0, that's 0, minus 1, I end up with 0 on top. And if I plug in the limit as x goes to 0, I end up with 0 on the bottom. That's an indeterminate quotient, which means I can use L'Hopital, which tells me that that's equal to the limit as x approaches 0 of the derivative of the top, 3e to the 3x, minus the derivative of 3x, minus 3, minus the derivative of 1, which is 0, and then over the derivative of the bottom. I take the derivative of the top and bottom separately. This derivative here is 10x. If I go to take the limit as x approaches 0 again, I get e to the 0 power times 3, that's 3, minus 3, I still get a 0 on top, because remember, e to the 0 power is 1, so I've got 1 times 3, that's 3, minus 3 is 0 on top, 10 times 0 on the bottom, I still have an indeterminate quotient, means I get to use L'Hopital a second time. This is still the limit as x approaches 0, take the derivative of the top again, that's 9e to the 3x, take the derivative of the bottom, that's 10. I can already tell, since my denominator is a constant, that I'm not going to be an indeterminate quotient again. If I take the limit of this as x approaches 0, the denominator is going to be 10 no matter what. And at the top, if I take the limit as x approaches 0, it gets me 9. So the answer to 2a was 9/10. Okay, let's take a look at 2b. 2b was an indeterminate power. We were looking at the limit as x approaches 0 of 1 plus 2x to the 3 over x. If I take the limit of this, okay, as x approaches 0, I'm going to get 1 to the power of infinity. Because remember, x never equals 0, it just approaches. And 3 over something going to 0 is going to go to infinity. So this tells me that this is an indeterminate power. And so the first thing I need to do, if this is y equals, the first thing I need to do is take the natural log of both of these. So I'm going to take the natural log of the limit of y equals the limit as x approaches 0 of the natural log of 1 plus 2x to the 3 over x. Now I can use my properties of natural logs, which say that powers can come out in front, and this becomes the limit as x approaches 0 of 3 over x. Watch how I'm going to, well, I'll write this in 2 steps. 3 over x times the natural log of 1 plus 2x. Now remember, in order to use L'Hopital, I need to be an indeterminate quotient. And this is not quite set up. Right now it looks like a product of two things multiplied together. But pretty quickly I can write this as a quotient. The 3 is in the numerator, but the x is in the denominator. And now I have a quotient. So let's test to see if it's in indeterminate form. What happens as x goes to 0? Well, 2 times 0 is 0, plus 1 is 1. The natural log of 1 is 0 times 3. I've got 0 on the top. And as x approaches 0, I've got 0 on the bottom. That means I'm an indeterminate quotient, so I can use L'Hopital. So this is equal to the limit as x approaches 0. Now I need to take the derivative of the top. The 3 is a constant. Draw a line to separate this. The 3 is a constant that comes along for the ride. Now I'm taking the derivative of natural log of 1 plus 2x. The derivative of natural log of something is 1 over that something times the derivative of the something. And the derivative of 1 plus 2x is 2. So that's chain rule on the top to take the derivative. Now I take the derivative of the bottom separately. Derivative of x is just 1. Already I can tell that because the denominator is a constant, I'm not going to be in an indeterminate form anymore. Okay, let's see what happens as I clean this up and I take the limit as x approaches 0. If x goes to 0, 2 times 0 is 0, plus 1 is 1, so this is 1 times 3 times 2. The top is 6, the bottom is 1. That means that this whole thing goes to 6. But don't be too quick to put a box around that answer. Remember, what is 6? The natural log of y is equal to 6. Which means if the natural log of y is equal to 6, then y is equal to e to the 6th power. And so that was the final answer. E to the 6th power is the final answer for 1B. All right, guys, here's number 3. F of x is negative 2x cubed plus 6x minus 2, and we're on the interval from negative 2 to 2. The first question is, what were the requirements of the mean value theorem, and are all those requirements met? The requirements would be that it is continuous on the closed interval, negative 2 to 2. Yep, that's a polynomial, that's a continuous function, and also that it's differentiable on the open interval. Technically speaking, you can't be differentiable at the endpoints because remember the derivative is the limit from both sides, and so if you're at an endpoint, you don't have that other side. That's a minor technicality, but it is differentiable. Okay, I can take the derivative of this, and because it's a polynomial, it's a continuous function. So here in part A, I was looking for you to tell me you knew that it needed to be both continuous and differentiable, and that that was true. Part B asked you to find the average rate of change. That was between the two endpoints. Okay, you didn't have to graph this function, but essentially we're going from negative 2 something to positive 2 something. Okay, and I want to know the rate of change. What's the slope of the line between those 2 points? So the first thing you needed to do is you needed to plug in to find the coordinates. So if I plug in negative 2, okay, I end up with an answer of 2. Okay, if I plug negative 2 in for x here, negative 2 times negative 2 cubed plus 6 times negative 2 minus 2, I get an answer of 2. If I plug in positive 2, negative 2 times 2 cubed plus 6 times 2 minus 2, I end up with an answer of negative 6. So when I go to find the average rate of change, I am subtracting f of 2 minus f of negative 2 over 2 minus negative 2. I'm basically doing the slope formula. y2 minus y1 over x2 minus x1. Okay, and when I do that, f of 2 was negative 6, minus f of negative 2 was 2, And then 2 minus negative 2, right? Minus a negative gets me 4 on the bottom. So I end up with negative 8 over 4, or a slope of negative 2. So for part B, the answer for the average rate of change was negative 2. In part C, since we've met the requirements and we know the average rate of change, now we want to find the values that the mean value theorem promises. The mean value theorem promises that if you have a continuous and differentiable function, then somewhere in this interval, there is at least one place where the derivative is equal to the average rate of change. Okay? So what I need to find is I need to find f prime, and I need to set it equal to negative 2 and solve. Okay, so in part C, I needed to set f prime equal to negative 2 and solve. So what is f prime? I take the derivative here. I get negative 6x squared plus 6. That's my derivative. That has to be equal to the average rate of change. And the mean value theorem guarantees me there will be at least one place where I have a solution to this. And in fact, there end up being 2. If I solve this and I subtract 6, I get negative 6x squared equals negative 8. That means x squared is negative 8 over negative 6, which is positive 4/3, which means when I solve for x, I get plus or minus the square root of 4/3, or plus or minus 2 rad 3. I didn't specify that you needed to rationalize it. Some of you wrote plus or minus 2 rad 3 over 3. That's also correct. So I was fine with this answer. With this answer, some of you gave me the decimal, plus or minus 1.15. I would take that one as well. Both of these points are both in the interval from negative 2 to 2, okay? And they are both places where the derivative is equal to the value of the rate of change, the line between the endpoints. And that line had a slope of negative 2. That's problem 3. All right, guys, here's number 4. Here I was asking you to graph a function given some information about it. So the first thing is that we're on an interval from negative 3 to 3. We're a continuous function. Okay, the derivative is 0 for x equals negative 2 and 1. When f is of negative 2, that's a local max. F of 1 is an absolute min, and f of 3 is an absolute max. So here's what I was looking for with the graph. This is one possible example. So yours might not look exactly like this, but I did check to see that you were drawing me a continuous function and you went all the way from negative 3 to positive 3. If f of negative 2 is a local max and the derivative is 0 at that point, then somewhere here, wherever you put that point, it needs to be a local max. Now f of 1, the derivative is also 0 and it's an absolute min. So that would mean it's a local min and also an absolute min. So at 1, it needs to bottom out. Okay, the derivative needs to be 0, but this needs to be the lowest point on the graph. So I don't want to see, by the time you get to negative 3, it should not go below this point. Okay, the other thing was that at f of 3, you had an absolute max. So if I drew my local max here, then my absolute max at 3 needs to be something that's higher than that local max. And then all I was looking for is that you would connect this from negative 3 to positive 3. So let's say I start here, I go up to my local max, I come down to my absolute min, and I go back up to my absolute max. This did not have to level out here. You could have come straight into that point. I didn't say anything about what the derivative was when x equals 3. But this is one particular example for what the graph could look like for number 4. All right, here's problem 5, probably the longest problem of the exam. F of x was 1/3 x cubed minus 2x squared minus 45x plus 2. First thing you needed to do in part A was find the y-intercept. That's when x is 0, so if I substitute 0 in for x, all I'm left with is 2. So the y-intercept was 2, or you could write it as the point 0, 2. The reason I had us do this is it just helps, it gives us one more point to put on the graph. The second part was to differentiate f of x, so find f prime, and then find the intervals of increasing and decreasing. So if I take the derivative here, I'm going to end up with x squared minus 4x minus 45. And if I want the intervals of increasing and decreasing, I need to figure out first, where is that derivative equal to 0? Well, this is factorable. It factors into x minus 9 times x plus 5 equal to 0, which means that the derivative is 0 at 9 and negative 5. That tells me that I can break up my number line at negative 5 and 9, and I can see, okay, well, if the derivative is 0 at these points, what happens to the left and right of these points? Because that's going to tell me where I'm increasing and decreasing. So I pick some value to the left of negative 5, say negative 6, and I plug in. Negative 6 minus 9, that's going to give me a negative. Negative 6 plus 5, that's also going to give me a negative. So negative times negative is going to be positive. So my derivative is going to be positive for all values to the left of negative 5. That means that my function is increasing. Okay, it's headed up in this interval. Now remember, at negative 5, the derivative is 0. But what happens between negative 5 and 9? So let's say I pick something in the middle, like 0. If I plug in 0, I get a negative. Here I plug in 0, I get a positive. Negative times positive is a negative. That means that my function is headed down. If the derivative is negative, your function is decreasing. Then I try something at 9, remembering that at 9, again, the derivative is 0. So I was increasing, I went to 0. Now I'm decreasing, the derivative is back at 0. Now, most likely, what we're going to see is that I'm increasing again. What if I pick a value to the right of 9, like 10? If I plug in 10 here, I get a positive. I plug in 10 here, I also get a positive. So my derivative is positive, which means my function is again increasing on this interval. So my intervals for increasing were from negative infinity to negative 5. And also, you could use the u, although I wasn't picky about that, from 9 to infinity. Okay? And then I am decreasing in the middle on the interval from negative 5 to 9. Okay? So those are my intervals of increasing and decreasing. Now, in part C, you basically use this information to classify the critical points. So negative 5 is a critical point. Negative 5 something, we'll come back to that. And 9 something is also a critical point. And I want to classify those. Well, if I'm increasing and then decreasing, then that creates a local max. So at x equals negative 5, I have a local max. If I'm decreasing and then increasing, that creates a local min. So at x equals 9, I had a local min. Now, how do I figure out these two, the somethings here? If I want the y coordinate, I plug back in to my original function. And if I plug negative 5 into this function, you do get a fraction, okay? It's 135.3 repeating, or 135 and a third, okay? Or 406 thirds, okay? That was another way to write it. If I plug 9 in, I end up with an answer of negative 332. So I have a local max here, and I have a local min here. That was the answer for part C. Okay, part D was to put this together on the graph. Okay, so I was looking for a basic sketch that showed me 1, 2, 3, 4, 5. There's negative 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's positive 9. Now, some information that I have is I know that I have a y-intercept of 0, 2. I know I have a local max here, and I have a local min here. So these are 3 points that I can put on the graph, and then I can use this information about increasing and decreasing to complete that curve. So knowing that I have a pretty large local min, my scale on the y-axis is going to have to be pretty big. So let's say I go by hundreds. Here's 100. Here's 200. Then I'm going negative 100, negative 200, down to negative 300, negative 400. Okay, because I've got to plot these points that are pretty wide. And so a y-intercept of 2, when this is 100, is going to be pretty much right here. I mean, barely off the origin. Okay, now the point negative 5, 135.3, is going to be somewhere about there, more or less. And 9, negative 322, is going to be somewhere down here. Okay, now I know that's a local max, and this is a local min, and there's a y-intercept. So I'm going, and this also helps me. I'm increasing, then I'm decreasing, then I'm increasing, right? So I'm increasing up to -5, this point here. Then I'm decreasing all the way down to 9, this local min here, headed through the y-intercept point, decreasing down, and then after 9, I am increasing again. So for part D, I was looking for a basic shape that looks something like that. Now the last step in this problem, I'm going to erase what I have up here, is part E, which is the second derivative and concavity. So the second derivative is the derivative of the derivative. So if I take the derivative of x squared minus 4x minus 45, I end up with 2x minus 4. Okay, I set that equal to 0, x is 2. That means that if I look at a number line, 2 makes the second derivative 0, and I want to explore, just like I did here, what happens to the second derivative on either side of 2. So if I plug in something to the left of 2, like 1, what happens when I plug it in here? 2 times 1 is 2 minus 4, that's going to give me a negative. And if the second derivative is negative, that tells me that I'm concave down. Now what if I plug in something to the right of 2, like 3? 2 times 3 is 6 minus 4, that's going to give me a positive, and when the second derivative is positive, my function is concave up. So that means that I am concave down for part E on negative infinity to 2, and I'm concave up on 2 to infinity. And that's the end of problem 5. All right, guys, here's our last problem, number 6, using what we know about antiderivatives and indefinite integrals. I need to take the indefinite integral of 6x squared minus the square root of x plus 5x to the negative second dx. I'm going to basically be using the power rule in reverse for each of these terms. So it might help to write the square root of x as x to the 1/2. If I take the antiderivative, remember the power rule in reverse says I up the power by 1. So now this is going to be x cubed, and then I divide the existing coefficient by that new power. So this first term is going to become 2x cubed, and I can check my work by taking the derivative, because the derivative of the antiderivative should get me back to the original function. If I take the derivative of 2x cubed, I get 6x squared. So I'm on my way. I'm going to do the same thing to the negative x to the 1/2 power. I'm going to up my power by 1, so now it's x to the 3/2 power. I'm going to divide by that new power. Well, dividing by 3/2 is like multiplying by 2/3. You could have kept this as x to the 3/2. Another way to write that is the denominator tells you what kind of a root you have. So I have a square root, and then the numerator is the power. So this is also the square root of x to the 3rd power. Most of you kept it as x to the 3/2. A few of you rewrote x, the square root of x cubed as x rad x. That's another way of writing it, so I accepted that answer as well. But probably the most common way of writing it was just keeping the fractional exponent x to the 3/2. Lastly, I'm going to take the antiderivative of 5x to the negative second. If I up that power by 1, now it's x to the negative 1st power, and I divide by that, which ends up with negative 5x to the negative 1st power. It was fine to write it like that. Some of you changed that. X to the negative 1st is also like dividing by x. I accepted it either way. And then don't forget plus c, our constant of integration. Because remember that if I take the derivative of this, I got to get back to here, and the derivative of any constant is 0. So for an indefinite integral or a general antiderivative, you always need to have that plus c. Okay, that was 6a. Let's look at 6b. Okay, problem 6b was solving, 6b, was solving an initial value problem. F prime was sine x plus 5, and f of 0 was equal to 2. So the first thing I need to do is find f of x, which is meaning that I need to take the antiderivative of sine x plus 5. Okay, the antiderivative of sine is negative cosine. Because if I take the derivative of negative cosine, I get back to positive sine x. And the antiderivative of 5 is plus 5x. Plus any constant c. Hey, this is my general antiderivative, but now that I know an initial value, I can actually solve for c. So f of 0 is negative cosine of 0 plus 5 times 0 plus that constant c, but it has to have a value of 2, and this allows me to solve for the constant c. Cosine of 0 is 1, so this is negative 1. 5 times 0 is 0. Negative 1 plus c is 2, which makes c 3. That means my final answer here was plugging back in that value for c. So f of x is negative cosine x plus 5x plus that constant that I solved for, which is 3. And that's the final answer for 6b.